Hi, I'm Jannis, and I will be talking about polygonal billiards in hyperbolic space. So we are interested in periodic billiard orbits in arbitrary polygons, and more specifically in hyperbolic triangles, as we will see later on. So what is a billiard orbit? It's basically the same as in Euclidean. So we look at geodesics, we look at basically geodesic flow, um, which is reflected on sides of the polygon. And that's how we get orbits. And we're interested in ones that are periodic, so they go back to where they started. So we can characterize these orbits by recording which sides they hit in which order. So for instance, given this periodic orbit, we see that let's say it starts at side 0, then afterwards it hits side 1, side 2, side 4, side 3, and so this will give us a code of 0, 1, 2, 4, 3. And now we can turn this around. So given some triangle and some code, we want to get an orbit, basically. And in this case, as you can see, this works perfectly well, but this is not true in general. So if I alter the triangle just slightly, you see that it breaks. And so we conclude that a given code works for some, but not all triangles. And so the goal is to kind of quantify this notion. And we do that with what are called orbit tiles. So looking at the parameter space, we have 3 degrees of freedom, which are the angles of the hyperbolic triangle. They have to be non-negative, and their sum needs to be less than pi. And so we get the simplex on the left. And now given a code, for instance 0, 1, 2, 1 in this case, we can sample a lot of points and see if that code works for the corresponding triangles. And out comes this picture on the right. So in the previous semesters, we worked on a sampling method, which gives us an approximation of these orbitiles. And this semester we focused on actually describing the surface of these orbitiles rigorously. And so on the right here you can see things that we did at the beginning of this semester, which were first attempt at describing the surface of these tiles. And now I will show you some of what we've been up to since then. So on the one hand, we've gotten very good at plotting this special case where one of the angles is equal to 0. That's a notion that doesn't make a lot of sense in Euclidean, but it makes actually perfect sense in hyperbolic space. So one of the angles can just be 0. We see it in this parameter space basically as one of the sides of the parameter space. So if you just take the slice where one of those angles is equal to 0, we've gotten very good at plotting that, and so we've played around with that a bit, as you can see here. So that's the one thing. And on the other hand, we've tried to refine our method for actually plotting the whole orbitile. And I can show you some of what we've done here. So for instance, this plot here, it's supposed to be, it corresponds to the code 123, which I can show you over here. The orbitile is supposed to look like this. So it's basically a cube with one side chopped off. And this is what we're getting so far. So it looks quite good. It's very close to it, but it's not fully there yet. So there's still some kinks to iron out in our method. Going further down for this code 0121 that we looked at earlier. So this one. Well, on the one side it looks rather convincing if you know what you're looking for. I know it's not very pretty, but well, in general it doesn't quite work yet. So that's basically what we're working on at the moment, and that's where work still needs to be done. So in the future we hope to improve our method of describing these orbitiles in order to study them more systematically. And then as an edge case we actually get Euclidean triangle billiards. And so the hope is to understand the Euclidean dynamics better by studying the hyperbolic billiards. All right, thanks for listening.